To simplify dynamical equation further, let us define the projector's pi epsilon for a non-degenerate system Hamiltonian HS. Non-degenerate means the eigenvalues do not repeat for the Hamiltonian HS. For that, pi epsilon will be just psi epsilon, where HS psi epsilon is epsilon psi epsilon. That is, psi epsilon are the eigenstates of the Hamiltonian HS with corresponding energy epsilon. But if the Hamiltonian is degenerate, then we can have more than one eigenstate corresponding to the same energy, and the sum over all those projectors having the same energy, we are calling it just one projector, pi epsilon. So pi epsilon is the eigenprojector of the system Hamiltonian HS, and we can write HS pi epsilon is epsilon pi. So we are defining the projector's pi epsilon in this way, and sum over epsilon, pi epsilon will be sum over identity, because this will contain all the projected rank 1 projectors over the eigenstates of HS, and HS is a Hermitian operator, so the eigenvectors forms a complete and orthonormal basis, and this becomes a completeness relation. Next, we define A alpha of omega to be pi epsilon A alpha pi epsilon prime sum over epsilon and epsilon prime, such that epsilon minus epsilon prime minus epsilon equals omega. So we take the projector of A alpha from the left on pi epsilon, on the right on for pi epsilon prime, such that the difference between epsilon prime and epsilon is omega. So we take the sum over all those things and we call it as A alpha omega. We can see that A alpha omega dagger becomes epsilon prime pi epsilon prime A alpha pi epsilon. All three pi epsilon prime and A alpha, all three are Hermitian, but when we take the Hermitian conjugate, they change their positions, but they remain the same. So this is our dagger of Hermitian conjugate of A alpha omega, and this is nothing but A alpha of minus omega. HS of A alpha omega will be HS A alpha of omega minus A alpha of omega HS. Here this will be HS sum over epsilon prime pi epsilon A alpha pi epsilon prime minus sum over epsilon prime pi epsilon A alpha pi epsilon prime HS. HS acting on pi epsilon will give us epsilon. HS acting on pi epsilon prime will give us epsilon prime. So we get epsilon minus epsilon prime, the A alpha of omega, which is minus of omega A alpha of omega. Similarly, HS A alpha dagger omega will be omega A alpha of omega. We can see such examples of such operators. For example, we have the A and A dagger, the annihilation and creation operators for a harmonic oscillator. From here, we have number operator A dagger A, which is n. The commutation of A and A dagger is 1. Now, from here, we see that A dagger A and A is minus A, and A dagger A with A dagger is A dagger, and this is same as here, just omega becomes 1. So if we had a Hamiltonian HS to be h bar omega times n plus half, that is the Hamiltonian of the simple harmonic oscillator, then HS with A will be h bar we are putting to be 1. If we put it to be 1, it will be minus omega a, and hs with a dagger will be omega a dagger. So this is a very well known example of such operators, a alpha omega and a alpha omega dagger. Since sum over epsilon by epsilon is identity, that is the completeness relation, say that a alpha is sum over epsilon by epsilon, a of alpha sum over epsilon prime by epsilon prime, and this can be written as sum over omega and sum over epsilon minus epsilon prime equals omega pi epsilon a alpha pi epsilon prime, and which becomes sum over omega a alpha of omega. So in that way, a alpha can be decomposed as the combination of a alpha omega for all the omega. Now a alpha of t, which is exponential of I hs t, a alpha exponential of minus I hs t. The a alpha of t was the operator, system operator in the interaction picture, and by definition it is given by exponential of I hs t, a alpha exponential of minus I hs t. This can be written as exponential of I hs t sum over omega a alpha of omega exponential of minus I hs t. Summation can be taken out, sum over omega exponential of I hs t a alpha of omega exponential of minus I hs t. This expression exponential of I hs t a alpha of omega exponential of minus I hs t, it can be expanded as a alpha of omega plus I hs a alpha of omega times t plus I t square over 2 hs commutator a alpha of omega, and so on. This is called BCH expansion. This is called BCH formula, and we can see that hs a alpha omega is minus of omega a alpha of omega. So the whole thing can be written as a alpha of omega plus or minus I omega a alpha of omega plus I t square over 2 factorial omega square a alpha of omega, and so on. We combine it all, it becomes exponential of minus I omega t, there is a t here sitting, a alpha of omega. So the whole expression, this complicated expression, can be written in terms of exponential of I omega t, a alpha of omega, hence a alpha of t is sum over omega exponential of minus I omega t a alpha of omega. Similarly, a alpha dagger of t can be written as sum over omega exponential of I omega t a alpha dagger of omega, which is sum over omega exponential of I omega t a alpha of minus omega, and since a alpha of t is Hermitian, this is same as a alpha of t. From here we can say sum over omega exponential of minus I omega t a alpha of omega is same as sum over omega exponential of I omega t a alpha of minus omega. It may not seem so, but this is a huge improvement over, this is a huge simplification for our dynamical equation, which will be apparent very soon. So let us write the interaction Hamiltonian, sum over alpha and omega, a alpha of omega, tensor b of alpha. HIT becomes sum over alpha and omega, a alpha of exponential of minus I omega t a alpha of omega tensor b alpha of t. From here, the dynamical equation rho s dot at time t becomes minus 0 to infinity d tau, which was trace over bath hi h at time t, commutator h at time s, rho s t tensor rho b. There's a trace over the bath degree of freedom, and we can write it as 0 to infinity d tau sum over alpha, beta, omega, omega prime, exponential of minus I omega t minus tau, exponential of minus I omega prime t, a alpha of t, a alpha of omega, rho s t, a beta of omega prime times c alpha beta t minus t comma t minus tau minus exponential of minus I omega t minus tau, exponential of minus I omega prime t, a beta of omega prime rho s, a alpha of omega rho s of t times c beta alpha t minus tau at t plus Hermitian conjugate of the two terms. So if we go back to our original equation after replacing the Bath operators with the 2-point correlation functions, and we substitute a alpha of t and a beta of s. First we replace by t minus tau, and then we replace a alpha of t as sum over omega exponential of minus I omega t a alpha of omega. Then we get this equation, and we are using a Hermitian conjugate so that we don't need to repeat the terms again and again. Hermitian conjugate will be the complex conjugate of the complex numbers and Hermitian conjugate of the operators. Now let us define, to make this expression look a little bit more simpler, let us define capital gamma alpha beta of omega as 0 to infinity d tau exponential of I omega tau, the expectation value of b alpha t b beta of t minus tau. So we are defining the Fourier transform of the 2-point correlation functions as gamma alpha beta of omega. Since rho b is time independent, that is a steady state. This was the Born approximation that the state of the bath does not change with time, so it's time independent, so it's a steady state. The bath correlation functions b alpha of t, b beta of t minus tau is same as b alpha of tau, b beta of 0. So the time translation does not matter here. So these two are same. So the Bath correlation function, the Fourier transform gamma alpha beta omega does not depend on t. It depends only on tau and the omega. Using this, we can write rho s dot t to be, so what we have done is we have consumed omega tau, this term, from first expression and second expression. We have consumed this term with c alpha beta to get the gamma alpha beta. So with this, we have a little bit simplified version of the equation, and that is omega prime sum over alpha beta a alpha exponential of minus I omega minus omega prime t gamma alpha beta omega a beta omega a alpha omega prime rho s at time t a alpha omega prime minus a alpha omega prime a beta omega rho s t times gamma beta alpha plus summation conjugate. So we have replaced the integration over tau. We have absorbed the integration over tau in the definition of gamma alpha beta, and we get this expression. Now consider the expression exponential of minus I omega minus omega prime t. This expression depends on the frequency of the system omega and omega prime and the time of evolution t. So if the frequencies are optical frequencies, let us say, so omega, if it is 10 to the power 14 to 10 to the power 15 hertz, and omega prime is also of the same order, but the time of the evolution is typically a nanosecond or a picosecond, so it's between 10 to the minus 10 to 10 to the power minus 9 seconds. So the product of omega times t is a very large number, and exponential of that very large number is a very, very fast oscillating term. This term for these typical values will be a very, very fast oscillating term. So the average effect of these terms on the evolution of the state will be nullified, and the average will be 0. So we will not see any dynamics of the system. But in the cases when omega equals omega prime or very close to it, then these terms can be discarded. And in such cases, we get rho s dot t becomes sum over omega alpha beta, because we are using omega equals omega prime, and the first term is discarded. Gamma alpha beta omega a beta omega rho s t a alpha omega minus a alpha omega prime a beta omega rho s of t plus summation conjugate. So wherever we had omega and omega prime, we are replacing omega prime with omega. So in general, the gamma alpha beta is a complex number. So we can write gamma alpha beta omega as half times gamma alpha beta omega, which is a real number, plus I s alpha beta, where s alpha beta is also a real number. So gamma alpha beta becomes capital gamma alpha beta omega plus gamma alpha beta omega star, which is given by minus infinity to infinity d tau exponential of I omega tau b alpha tau b beta 0. And we can write rho s dot to be minus I h ls, we'll define what it is, rho s plus d of rho s at t time t, where HLS is the Hamiltonian for lamp shift. It's called lamp shift Hamiltonian. It is given by S alpha beta A dagger alpha omega A beta omega sum over alpha and beta and omega. And this is called lamp shift Hamiltonian. Lamp shift is the shift in the energy levels of the quantum system caused by its interaction with the bath system. And we can see that here S alpha beta is the information we are getting from the bath correlation function. And A alpha and A beta are the operators of the system. So this is the Hamiltonian of the system caused by the Bath correlation functions. If the Bath correlation is 0, then this term goes to 0. And Bath correlations are 0 only when so this term will be 0 only when there is no interaction between the system and the bath. D of rho s is called dissipator. So this is a map acting on rho and given by sum over omega, sum over alpha beta, gamma alpha beta of omega, a beta of omega rho s of t, a alpha dagger of omega minus half anti-commutator of a alpha dagger of omega, a beta of omega rho s of t. So this is the simplest and final form of the dynamical equation we have now. First term is the lamp shift, which is caused by the interaction of the system with the Bath degree of freedom. And the second term is the dissipator, which results in the loss of the coherence and the quantum effect in the system. Both of these terms are coming purely because of the interaction of the system with the bath. And let me remind you that this whole thing is in the interaction picture. After solving this dynamics in the interaction picture, we can go back to the Schrodinger picture and find the dynamics of the state in that picture. Just last remarks. It can be proven that if we consider matrix G, which contains gamma alpha beta. Okay, so the gamma alpha beta are the real numbers, and for different alpha betas, we can make a matrix G. Then it can be proven that this is a positive semi-definite matrix. What does it mean? It means G is Hermitian and the eigenvalues of G are always non-negative. It means G can be written as sum unitary times U times D times U dagger, where U is unitary and D is some diagonal matrix. And let us say D's are gamma 1, gamma 2, gamma n. It means gamma alpha beta can be written as U alpha I Dij U dagger J beta and sum over I and J. This can be written as this is equal to sum over Ij U alpha beta I U star beta J Dij is gamma I delta Ij. And we can just remove the sum over J, replace all the J's with I's and remove the delta function. So gamma I alpha beta is U alpha I U star beta I gamma I. Substituting it in the dynamical equation or in the dissipator, D of rho S becomes sum over n and omega gamma n ln rho S ln dagger minus ln dagger ln rho anti-commutator rho S, where ln is defined as sum over alpha U alpha I A I these are called Lindblad operators. So if we consider only the dissipative dynamics of the system and forget about the lamp shift, then rho dot can be written as sum over n gamma n ln rho s ln dagger minus half times ln dagger ln rho s anti-commutator. There is a half factor here missing, so half times ln dagger ln rho s. So this becomes our final dynamical equation of the system when it is interacting with the bath. We have made certain approximations, but with those approximations we have achieved Markovian master equation for the dynamics of a system interacting with the bath. This is also called Lindblad master equation.